equality? Is it just a theoretical fad or does it have practical implications? In this video I will show you that we can use the tools we have developed, such as subst and sim and trans, in order to write quite concrete programs. So to do this, let's start by looking at lists. So you can reverse a list in this naive way, which you might remember from Haskell, where you're saying that the reverse of the empty list is the empty list, and reversing a non-empty list, we first reverse the tail, and then we take the head and we stick it at the end of it, right? And you can try this and you'll see that this works exactly the same for vectors. But for lists, there's also a more clever way to do it, where instead of doing this concatenation each time, which is quite costly, hence the high complexity of the function, we can use an accumulator to get the complexity down to linear. So the way this works is that if we have the empty list, then we just return the accumulator, and if we have a non-empty list, then we stick the head on the accumulator and we continue. So next time we're going to stick something in front of this, and that's going to reverse the list eventually, right? So let's see if we can do the same thing for vectors, which you might remember as the length indexed lists, right? So we're trying to do the accumulating version, so I'm going to call it revac for accumulator. And the first thing we have to see is we have to have the right types. So if I have a vector of length n, which is going to be my accumulator, and I have a vector of length m, which is going to be my list that I really want to reverse, then what am I going to get in the end? Well, I'm claiming I'm going to get a vector of length n plus m, because we're going to take all the elements from this list and stick them on the accumulator. So if we started with n elements, we're going to have n plus m in the end, right? Okay, so let's see how we get on. How do we define this? Well, we want to do it the same way as here, probably. So we pattern match on the x's. Okay, and then here in the empty list, we have to return something of this type. And if we look at what we did for the list, we should just return the accumulator. But then we see that we get a type error, because what we want is something of type n plus 0. That's what we said here, right? But what we have is something of type n. We saw earlier that n plus 0 and n were not obviously the same thing, right? But we did have a proof from last time which shown exactly that n plus 0 and n is the same thing, right? So I will copy paste this. It's a bit bigger while we're at it. So I do have this proof which I can apply to n, which makes things fit. So I could either rewrite by this, or I can show off my subst function, which tells me that if I have something with matches except for an equality like this, then I can go from one to the other, right? So let me substitute. The thing that doesn't quite fit is vec of a, and I don't know what my proof is yet. I just leave it like this. And the thing I have that I would like to fit in is this accumulator, right? Okay, so that works, except we don't know what this y is yet, but that will become clear when we give the proof. Okay, so here we see that we have to prove exactly the equation that was missing, and that's what this thing is doing. So really here I need to give the n, but the n is not in scope, so I'm just going to give an underscore to tell Agda to go and figure it out. Okay, and we see that this doesn't quite work because my equation is left to right, but what is needed is right to left. So I'll have to stick a sim in front of this, and then it goes the right way around. Okay, so we managed to give back the thing we wanted by fixing up the type using subst. So let's see what's happening for this one. So here we would just like to make a recursive call with we stick the x in front of the accumulator, and then we do the access. So let's see what happens if we do that. And then we see that that almost works again, except that this suck is in the wrong place. Right, so again, we can do the subst to correct in the type of A. I don't know what the proof is, but that is what I would like to return. Okay, and now here I have to give this proof that a suck of a sum is the same as a sum of an n and a suck on the right. Okay, so let's go to the last lecture and see if we had something like this. It looks a lot like this proof, right? Except that again, this one is going to be the wrong way around, so it's going to be sim of something. And now I can do this of two things, and it fits. Okay, and then we can finally define the reverse for a vector as the thing where we instantiate the accumulator to be the empty vector. Right. Okay, and if we now test this, let's say that I want to reverse the vector 1, 2, 3. Okay. Right, so complaining that I had an implicit argument which is not determined because I forgot to delete it. Okay, now it knows what the type is, and if I normalize this, Control C, Control M of test, then I get 3, 2, 1. So in particular, notice that these subst have disappeared, right? Because these proofs here have, if you look at their definition, they're going to compute down to refl for these concrete cases, and then if we go back, subst of refl is exactly the identity function. So these proofs don't actually get in the way when we evaluate things on concrete things, so we can still run our programs and get concrete things out, even if we do this. So what have we learned? Well, we can use subst to fix up the types when things don't work out as well as we could. It's always nicer if you don't have to use subst because it's a faff, but life is not always easy. And right, I should also point out that sometimes we can use rewrite instead of subst, right? But subst is something that works all the time. Rewrite only works all the time, 60% of the time. Okay.